All the previous videos in this series have led up to this equation to find a solution U in the space H10 such that some bilinear functional equals a linear functional for all functions W in that space. And we talked about functionals, right? This involves functionals. We talked about these function spaces that we're seeing here. And we saw that partial differential equations have can be written in this way. So next what we're going to do is we're going to analyze this equation and hence coming to the point of functional analysis. We're going to try and answer a couple of questions in relation to this statement. And so for instance, a question that we could pose ourselves is, can we find does a solution U actually exist based on this statement? So that'd be the question, can I solve this? Which involves the existence of a solution. Another question might be, given that a solution exists, is it the only one that exists? So is there a unique solution? So is there only one solution? This involves uniqueness. Another question that might be very interesting coming from our course name on stability of finite element schemes is, how sensitive is the solution to the data? That revolves around the concept of stability. So I'll number these questions, and in this video and the next videos we're going to address each one of these. We'll actually see that this involves two new concepts, two new mathematical concepts. The first one is that of coercivity, and the second one is that of boundedness. And these are two terms that have relevance to bilinear or linear functionals. So I'll just write down two definitions and we'll see what this is actually about. So each of these questions will revolve around the coercivity of B, our bilinear form, the boundedness of our bilinear form B, and also the boundedness of the linear form. Yeah, so these are somehow properties of B and L. And as we saw that partial differential equations are encoded in B and that all the boundary data and are forcing either Dirichlet data, Neumann data, that all follows in L, this also then involves our prescribed data. So the coercivity of B, the boundedness of B, and the boundedness of L. So what are these terms? What do they mean? Well, there's actually just very simple definitions of what a coercive bilinear form is. A coercive bilinear form is a bilinear form that takes two functions u and u and will always produce a value that is larger than or equal to some constant, which we'll call the coercivity constant, subscript c, times the norm of u square. And this has to be true for all functions u in, well, let's stick with the example of H1 as our space. So that means that this norm, well, we know that norms change from space to space. If we have this bilinear form set in with these functions in H1, then naturally we will also have to take the H1 norm. So this is just a definition, and we'll try to get a little bit familiar with this definition while we try to answer these three questions. But for now, just take it as a definition. If we plug the same solution, the same function into the bilinear form in both slots, then whatever pops out, right? This is a functional, so it takes a function, it produces a number. So if I give it twice the same function, then the number that it produces will always be larger than or equal to some constant times the norm of these functions squared. So it's a property of B, some property. Now we have a boundedness, which is sort of almost the opposite. This is that if we substitute two different solutions, U and V, then whatever value pops out, it will be smaller than or equal to CB times the norm of U. Oh, there was a V. U measured in the H1 sense times the norm of V, also measured in the H1 sense. And again, for all functions U and all functions V in their respective spaces. So where the coercivity says something about sort of a minimal value of B, the boundedness says something about sort of a maximal value of B. And then boundedness also kind of translates to linear forms, so it doesn't only involve, it doesn't only exist in the context of bilinear forms, also for linear forms, where it's a pretty natural extension. So if we take, we plug in some function U, then that's going to be smaller than or equal to CL times the norm of U measured in H1. And again, for all U. Okay. So, as I said, these are just definitions. At first, they might look a little bit overwhelming or strange. As we try to answer these questions, we'll get a little bit more familiar with what these definitions mean. And I can already tell you they're going to have to do something. They're going to have parallels with minimal eigenvalues or maximal eigenvalues. In that sense, there's a strong relation with the stability of the differential operators. And yeah, these are things that we'll see in this video and the next ones. Okay, so in the rest of this video, I'll actually proceed with question number 1. So we're going to try and answer question number 1, which was on existence. So we're trying to prove that a solution U exists such that this holds true, that this equality is true for all functions W in H10. Now, in principle, that does not involve a finite element method. This is just a statement set in Sobolev spaces, infinite dimensional Sobolev spaces. I have not introduced any form of discretization, right? This is not a finite element method yet. This is a very pure mathematical equation on the existence of a solution to a partial differential equation. Now, nevertheless, in order to kind of get a feel for the reason for why existence can be proven in the way that we'll end up doing, I'll actually move to a finite element context. I feel like that's the more intuitive way of looking at this. So, and afterwards we'll get back to the original statement. So let's jump ahead to the discrete form. So what do we mean by a discrete form? Now, again, the Sobolev spaces are infinite dimensional. And that means that there's infinitely many functions in the Sobolev spaces. Now, discrete means the opposite of infinite. That means that it's finite dimensional. So we're going to build a new space, which is a subspace of H1. Let's make it a subspace of H10. And this space will be finite dimensional. So the dimension of WH is smaller than infinity. And in fact, we're going to construct this space WH as the span of a set of basis functions n of x. From I is equal to 1 to I is equal to big N. Yeah, that's the number of degrees of freedom, essentially. So that's precisely what we do for a finite element method. Take a one-dimensional domain here for a quick example, run it from 0 to L. And what we do with the finite element method is we have these head functions. And if we have a higher order polynomial basis, then these might look a little different, but the idea is always the same. We have a set of basis functions, and then we're going to say that any solution U of our finite element problem, so UH, a discrete solution, which is a function in my discrete function space WH, that can be written as the sum from I is equal to 1 to big N of coefficients U hat I, times these basis functions. So we'll write any solution U to be the sum of a weighted sum of these little hat functions. And a weighted sum of basis functions means that the space WH is spanned by these basis functions. And a span means that I can take any linear sum of whatever is in the span, and that will still be inside of the space. Now, so this is a concept very similar to that of a vector space that we talked about before, where the linear combination of any components in that space are also in that space. In this case, it is about the span of basis functions. Any linear combination of these basis functions will be a member of the space WH. Okay, so let's rewrite this statement a little bit. One way of rewriting this is that we're going to create now a vector of coefficients and a vector of basis functions, and then the sum is simply a matrix multiplication of a vector transpose multiplied by a vector. So we could write this as a vector of these coefficients U transposed by now a vector with all these basis functions evaluated at point X. And this is completely identical. So given that representation of some solution UH in our discrete function space WH, what does coercivity mean? What does coercivity mean? So we have here this funny definition that if we substitute the same function in both slots, then it has to be larger than or equal to something like this. So let's try to do that with this representation of our function U. So we're going to substitute B, we're going to substitute our UH in both slots, which we write, so UH and UH, which we write as this vector matrix multiplication, or vector-vector multiplication. U hat T and X. And for this one, I'll actually do it the other way around. So that's going to be the exact same thing. I hope you see that. And these U hats, they're just vectors with values. These are independent of X, which means that I can sort of pull these out, which only leaves the vectors nx, which is just a sum over different basis functions from I is 1 to I is the number of degrees of freedom. And that's how we end up with this statement. Where B is now a matrix of values where we have substituted the ith and the jth basis function. Also, we've changed our bilinear form acting onto functions into a matrix where we're pre and post multiplying by a vector of coefficients. And that's equivalent in our discrete function space WH. So what does now this definition of coercivity effectively mean? So we have UH is going to be larger than or equal to CC times the norm of UH square. Well, let me substitute my obtained definition of B UH, and then we obtain that U transpose B U divided by the norm of UH is going to be larger than or equal to square, sorry. It's going to be larger than or equal to this constant, CC. Now, this is a slight abuse of notation, but in finite dimensional function spaces, I'm actually allowed to manipulate this in a sense that makes this equivalent. But this is something that you might recognize. This is the Rayleigh quotient, or some definition thereof. And this is actually a property of now the matrix B. This is the property that the matrix B is positive definite. Specifically, this constant C has to be larger than 0. I'm not sure if that was clear or not. So I can actually rewrite this a little bit and get a definition of CC. If this has to be true for all functions u that I input, then CC has to be the minimal value of all potential candidates. And this is going to be, in my notes I wrote the maximum eigenvalue. Does that make sense? Pretty sure this is going to be the minimal eigenvalue of B. And B is actually the finite element stiffness matrix. Yeah, so I hope that that's something you recognize from this, because this is exactly how we define a stiffness matrix. So coercivity is saying something about the minimal eigenvalue of our stiffness matrix, and in that sense specifically that our stiffness matrix is positive definite. Positive definiteness is a guarantee of having an inverse for a matrix. So if a matrix is positive definite, then we know that it has an inverse. And so in this discrete setting, coercivity, positive definiteness, means that we can indeed obtain a solution. And if we have an inverse of the matrix, then we know that a solution exists. So that's an important conclusion here. Coercivity, that funny property that we defined before, has a strong relation with the positive definiteness of a matrix. And positive definiteness is a sufficient, but actually not necessary, condition for invertibility. Of B. And thus solvability of the equation b times u is equal to f. Now, if we know b has an inverse, then we can multiply both sides of this equation on the left by b inverse, and then we get a solution for u hat. So in this discrete sense, coercivity is the only thing that we need to prove existence of a solution. And intuitively, we have this correspondence with the positive definiteness of a stiffness matrix. Now, that's something that we can only do in a discrete sense. We can only formulate a stiffness matrix in a discrete sense. We have here an iterator from I and j going from 1 to the number of degrees of freedom. If our spaces are infinite dimensional, our Sobolev spaces, right, there's infinitely many functions in our Sobolev space, then we would not be able to do this. But in a discrete sense, this is all we need. Now, to kind of just give you the answer for the general question then, so in the continuous setting, which means not discrete. It's a nice way of saying continuous, or a nice way of saying non-discrete is the continuous setting. We also require boundedness of B and L. So in a discrete setting, boundedness is guaranteed already. In a continuous setting, we have to prove this. Now, that is not a very strange, I'm not going to go into why this is, but it's in principle not a very strange concept, because what boundedness was saying was that we didn't get infinite values when we plug in different functions here. Yeah. So if this is always smaller than or equal to some constant times these norms, essentially that comes down to this not blowing up. Yeah, and intuitively it makes sense that that's something that we would require from our bilinear and linear forms, that we don't get infinite values. So yeah, and the last thing I would like to point out, this is actually a very famous result in our field. This is called the Lax-Milgram lemma, which is something that you might come across repeatedly. So that is saying that if we have a statement like that, the one that we started with, the bilinear form equaling a linear form, and the bilinear form is coercive, and the bilinear form and the linear forms are bounded according to the definitions that we saw, then a solution exists. And in fact, the Lax-Milgram lemma also says that the solution is unique. That's the thing that we'll talk about in a second. So this Lax-Milgram lemma, that's something that you might come across in textbooks or even in research papers, and that's what this refers to. Okay, so this is the extent to which I want to prove this. For the continuous case, clearly I haven't proven anything, and for the discrete case, I give you more sort of a flavor of why we need this coercivity property. I don't think it makes a lot of sense for us to go into more detail than that. I want to give you a feeling of what these properties mean. Yeah, we saw here that it sort of relates to the positive definiteness of the stiffness matrix, and I feel like that's pretty much what we need to understand to be able to move forward with the theory that we have in mind. Okay, I think that's it for this video. In the next video, we're going to answer question 2, which is on the uniqueness of this solution.